Today's lesson on the 14th of January is looking at harder questions that involve pulleys. Now I'm only going to do one example and get you to try two questions, just two questions, because they're quite long and I don't want to give you too much work. So I'll give you a quick run through for question 1 of the textbook exercise, and then you can do questions 2 and 3. So there's two parts to these questions, exercise 21 in the textbook. The two parts are, first part here is exactly the same type of question as the questions we did yesterday. So A, B and C, the acceleration of the system pulleys, we're using F equals ma for the two bodies. Then we're substituting in our acceleration to get T, and then we're just timesing T by 2 for part C. So whatever the two questions I'm going to give you, you should be able to do at least the first 3 parts, and I'm going to show you how to do the next 3 parts, D, E, N, F and G, even 4 questions, because they involve suvat. So the second part of the questions involve your suvat. So let's have a quick read through the questions. Two bodies A and B of mass 0.6 and 0.4 are connected by a light inextensible string which passes over a smooth fixed pulley. Particle A is 1.2 meters above the ground. That's a bit of new information that we wouldn't have got in the last exercise. So particle A is 1.2 meters above the ground. The system is released from rest, and that's important. The system is released from rest with the bodies hanging vertically. So like I said, 1, A, B and C, you should be happy enough with them if you're happy enough with yesterday's work. So 1, A, B and C is just this working out. So just notice the heavier object is going to fall down and the lighter object is going to be brought up. This is our F equals ma for our heavier object. This is our F equals ma for our lighter object, and then we work out the acceleration. We use that acceleration to plug into either of these equations, doesn't matter. So T minus 4 is equal to 0.4a, where we know a now, so we get the value of T, the tension. And then part C, I should have T here and T here. Part C is you're just doubling your answer for part B to get the tension pulling down on the pulley. Now the next part of the question is all about what happens after the system is released. So yes, we know that this heavier body is going to fall down. Eventually it's going to hit the ground. So it's going to fall down and it's going to hit the ground at some speed, some final velocity. And this object here, it's going to continue rising up even after particle A has hit the ground. It's going to continue rising up. So going back up to the question and just reading from here, when A hits the ground, the string becomes slack and B continues to rise. Assuming that B does not reach the pulley, find first of all the time it takes for A to hit the ground, then the speed of the bodies at the instant A hits the ground, then the additional distance B rises after it hits A, and the time that elapses between A hitting the ground and the string becoming taut again. We're going to focus first on D and E because they're both involving object A. It's asking us for the time it takes A to hit the ground and the speed that A hits the ground with. So my working out here, I've just a simpler drawing. I don't have any of the tensions, any of the forces, just a diagram just showing that A is going to fall this distance here. It's going to fall 1.2 meters and S is going to go up a certain distance. But we're only really concentrating on object A at the minute and the time it takes to reach the ground. So this is suvat, S-U-V-A-T. S is 1.2 because it's in the question. It tells us that A is 1.2 meters above the ground, so S is 1.2. U is 0 because in the question it says that the system is released from rest. So A is effectively dropped at a height of 1.2 meters. V, we don't know. V is the final velocity whenever it hits the ground. We don't know it, but we're actually going to be asked that in the next question. A is the acceleration of the system. The acceleration we use for this is from part A. We have worked it out because the acceleration whenever we release the system has been worked out in part A. And T, the time it takes to hit the ground, that's something that we are asked to find out right now. So just looking at what we have and what we need, we have S, U, A, and we're looking for T. So our equations of motion is just a good time to look back over them. V equals u plus at, v squared equals u squared plus 2as, s equals u plus v over 2 times t, and s equals ut plus a half at squared. So we have s, u, a, and 1 to t, so we're going to use s equals ut plus half at squared. Plug all of those things in, you'll get t squared is equal to 1.2, so take the square root. The time a takes to fall to the ground is 1.10 seconds. So the next part is the speed of the bodies at the instant A hits the ground. So A is going to fall this distance, 1.2 meters. It's going to take 1.10 seconds. What is its final speed? And bear in mind that it's going to be the same speed as B, so at that instant A and B will have the same speed. But we're just going to focus on A, the final velocity of A whenever it hits the ground. It falls 1.2 meters. It fell from rest. It fell, the acceleration is still the acceleration from the initial drop. We know the time. We have everything we need except for V, so we're going to use V equals u plus at. So when you plug it all in, the final velocity of V when it hits the ground is 2.2 meters per second. That's also the velocity of object B at that point in time as well. Now once A hits the ground, A stops. So when A hits the ground, it stops, but B doesn't stop. B keeps going up. So B has an initial velocity, and it's like it's being thrown up into the air. So even though A hits the ground and A stops, B continues to rise. Which is why in question F, it asks us for the additional distance that B rises after A hits the ground. So we're looking at a distance, we're looking at S, a height. Now what do we know? We don't know the height, that's what we're looking to find out. Now we know the initial speed of B. The initial speed of B is the same as the final velocity of A whenever it hits the ground. So we'll use our answer 2.2 from the previous question and set it as our initial speed, our initial velocity rather, for B. We've set the final velocity as 0 because we're looking at height, the maximum height, and whenever we have a maximum height, the velocity, the final velocity is going to be 0. It's going to stop moving. And because it's being thrown up into the air, whenever it's being thrown up, object B is going to start to slow down. The acceleration therefore is negative. This is the acceleration due to gravity, but it's negative because it's slowing down, because we're throwing it up. So we're looking at distance S. We have u, v and A. So we're going to use v squared equals u squared plus 2as. Sub it all in. The additional distance that object B rises after A hits the ground is 0.24 meters. G asks for the time that elapses between A hitting the ground and the string becoming taut again. So whenever B rises, the string is obviously not taut. The string is loose as it goes up into the air, and then whenever it comes back down again to its original position, it's going to be taut again. It's not going to be loose anymore. So really what we're doing here is we're saying that we know that object B is going to go 0.24 meters into the air with an initial speed of 2.2 and a final velocity of 0, and its acceleration. We know all of these things. So if we can say, well, we know all of these things, how long does it take to get up to its maximum height? Then we're going to double it, because the time up is the same as the time down. Whenever you throw an object up in the air, the time it takes to get to its maximum height is the same as the time it takes to get back to its original height. So what we're going to do is v equals u plus at to see how long it takes the object to get up to its maximum height, and then we're going to double it, which is where we get 0.44 seconds. So much more work in these questions, but like I said, the first ABC should be happy enough. That is, if you're happy with yesterday's work. The second set of questions is suvat. Now just notice for question 2 and 3, you might be given S or you might be given T. It could be different for every question, but it's still going to be suvat. So if I just show you the two questions that I want you to try, just two questions, and this PDF is going to be on Google Classroom. There's question 2 and question 3. So question 2, just treat it exactly the same way as the questions from yesterday. This is the same as previously. So that should be okay. Now just notice for question 2, it gives us t. The time is 1.2 seconds when it hits the ground. So then you'll use your suvat and remember that the initial velocity is 0. It's looking for s. You have a from the previous question. So it's the same type of question in that you're using suvat, but just you might have a slightly different bit of information to start you off. So have a go at 2 and 3. Take your time. I'm not asking you to upload it just yet anyway. I'm going to put up the solutions tomorrow, and then you can mark it and put up your marked work. So if you have any problems, let me know. But that's all I want you to do. Have a look over this question, question 1, and try 2 and 3.